with that context, let's get into the talk, which is small language models versus large language models for token classification. Do smaller models still outperform LLMs? And so the token classification task here that I want to talk about is named entity recognition, meaning let's extract named entities from unstructured text. Now, named entity is something like a name or organization or locations or specific entities in the text that probably need to be detected for a number of reasons. It could also be things like nationality or religious preferences, modifiers or adjectives about specific entities in the text, or it could be other kind of interesting nouns like diseases or medications or dosages of those medications. These are all examples of things that one would try to detect in the context of named entity recognition. And this is for a variety of purposes, like information extraction is one. I mean, imagine you have a clinical note and you want to extract the medications and dosages from that note into a machine parsable format. From our perspective at Tonic, we care about this from the point of view of protecting privacy. We want to be able to detect the named entities in text, things like personally identifying information, and then either redact or synthesize those entities. So the classification task here is basically, start with some annotation guidelines. In other words, descriptions of what the entities are, then take a text, and then that text we're going to break up into tokens or think words, and each of those tokens we're going to predict a label. The label is is this a person entity, or which entity, if any, in our guidelines does that token correspond to, and from those you can roll those up into individual entities. So the way we're going to frame our evaluation here and think about structuring this problem is motivated by the CONL, the Conference in Natural Language Learning kind of benchmark from 2003, which basically said it was a named entity recognition benchmark, which posited the following evaluation criteria. We should evaluate predictions based on spans, meaning an entity's start and stop location in the text, start and stop indices in the text, as well as their labels. So in the example of my name is Steele, my given name, which goes from characters 11 to 19, is G.Ander. That's highlighted in the light blue. My family name Steele is highlighted in that green, and that's from characters 20 to 26. And in order to be scored correctly with respect to this evaluation criteria, I would be required to produce two predictions with the same start and stop indices and the same labels. And so all these other predictions, even though they kind of overlap, are considered incorrect. The first example here, I've broken up G.Ander into two given names, which is not correct according to my ground truth labels or annotation guidelines. So there's a very strict kind of evaluation criteria. That's one thing to keep in mind. And I mentioned this CONL 2003 benchmark, which is basically extract names, locations, and organizations from Reuters headlines. And you can see the progress over time on this benchmark. It's kind of, over the past 10 years, you see basically this benchmark is kind of saturated around 0.94 F1 score. But there's a couple of interesting points here that are not reflected in this plot. The first interesting point is the release in 2019 of BERT, Google's basically small language model that could be fine-tuned for a variety of NLP tasks. So that you can sort of see here with this LCM CRF Elmo BERT Flare model, which is a combination of various techniques to get at the time kind of the best scoring model. But the other point, which is not visible here and which is interesting, is March 14th, 2023, when GPT-4 was released, we don't see a point here indicating that this benchmark has been solved by large language models, which may or may not be surprising, depending on how optimistic you are about LLMs. So, I'll talk a little bit about small language models introducing this cast of characters. By small language models in this talk, we mean fine-tuned versions of BERT or Roberta. So these are these encoder models that take sequences of tokens and produce sequences of vector embeddings for each of those tokens that represent not only what the token is, but what it's doing in context. And these are very powerful because you can take these vector embeddings and then build classifiers on top of those. And so in particular for the NER task, you can build classifiers on top of those token embeddings, which classify each of those tokens as one of our entities or not. And so in order to do that fine tuning, you need basically a large number of annotated samples of data. And these annotated samples, you need basically on the order of 1,000 examples of your entity in context. And the quality of inference on the fine-tuned model depends very much on like how good that training data was. So in particular, like you have to have enough data, and maybe it's 1,000, but like maybe for more complicated classes, it's many more. So there's no hard and fast rule here, but you need a significant amount of human labeled data to make this work. And these labels, of course, need to be internally consistent and correct. They need to follow the annotation guidelines. They need to be consistent across the many examples. And finally, like the data that you're using to fine tune this model needs to represent the data that you're going to be inferring on. A concrete example of this is basically, if you take a model that's trained on public web data like Spacey, and you try to use it to do inference on automatic speech recognition transcripts, which are not part of the training data, the performance will generally suffer quite a lot because the inference data is well out of distribution with respect to the training data. So your training data needs to be representative of the downstream task is the key point for how to leverage these things successfully. On the other hand, the other side of this, we have large language models, which, unlike BERT and Roberta, have been fine-tuned on much more, or not fine-tuned, have been pre-trained on much more data. They have essentially much more comprehensive world models, if you will, based on their pre-training on 100 to 1,000 times many more tokens. And these models appear to work well for a variety of information extraction problems. So they, this should totally work in principle, right? Like we've all seen demos of people using LLMs to kind of structure notes, like extract JSON kind of representations of text. And so, in principle, this should work. And we could even imagine this working even better if we provide examples in context, using few shot prompts. Basically we've all seen, we can engineer our prompts for LLMs to work well by, giving examples of inputs and expected outputs. So, like 2013 or 2023, we're thinking maybe NER is simply solved by GPT-4, but there are certainly lots of challenges with making that work in practice. And at the time, one of the big challenges was structuring the outputs, because we're basically predicting tokens here. We're predicting entities, which are substrings in our text. And so we have to like make this into a machine parsable list. The output needs to be some sort of like JSON or structured output. At the time, that was difficult to do, but now it's trivial. So this is a solved problem. All the major providers, of course, offer structured outputs. And if you're running your own model, you can, impose constraints on the generation to make sure that, you're essentially outputting the kind of JSON structure that you expect. Okay, so that's one problem solved, but there's still another problem, which is how do you localize entities in the text? And I'll give you two examples of sentences here where obviously a substring has many different meanings. So in this first sentence, if we were asked to extract like names and locations, which Washington corresponds to which? The Washington Monument in Washington celebrates the life and achievements of Washington. So, the second here is obviously location. The third here is person. So basically, whatever our prediction is, it needs to kind of indicate which occurrence of the string is what. All right. In this second sentence, which is like a famous pathological sentence of many different occurrences of the word buffalo. The first buffalo indicates like the region in New York. The second buffalo is the animal. The third buffalo is the verb for harassing. So these all have different meanings, even though they're the same word. So that's a problem that needs to be solved, because the output of LLMs is going to be tokens. So you need words. You need to be able to describe which word is what. Finally, like there's a general problem of like using LLMs. You need to basically align it to your intent. In this case, it means basically crafting good annotation guidelines that the LLM could follow. It's similar to how you might build annotation guidelines for human annotators. We have the same problem of describing what you want in a way that can be followed as a recipe. And so I'll talk a little bit about that, because maybe it's not obvious how hard this is in practice. So I'll give you a simple example of the instruction: tag all person names. If we were labeling names as AR, this already has like several questions that have to be answered. For example, does Dr. Watson include the prefix doctor? Should the president, which refers to a specific individual but not by name, should this count? Do we care that Dr. Watson is a fictional character? All these questions have to be answered. And of course, I have strong opinions on these because I've written annotation guidelines for these. And I personally think the answer to all of these questions should be no, but that's for my annotation guidelines. And now, the kind of point is that like when you're writing these annotation guidelines, it may be difficult a priori to figure out all these rules and edge cases. And so it's actually pretty important to kind of review the data as a source of edge cases and to formulate these rules. Okay, so with all that said about the challenges of using LLMs, now what I want to talk about some experiments where we compare the small language models versus large language models on a couple of different data sets and with a few different tasks. And the two different data sets that we're going to look at are one, public web data, which presumably is in the pre-training corpus of these large language models. These are things like Common Crawl samples or SEC filings. The data themselves probably belongs to the pre-training corpus, but the annotations are our own, and so it's reasonable to expect that those haven't been trained on. The second data set that I want to talk about is ASR transcripts, so automatic speech recognition transcripts. This is data that we reasonably believe not to be included in the pre-training corpus of any LLM. These are customer transcript conversations between like a customer support agent and a customer. These, of course, are rife with PII, things like payment information, names, locations, all that. And so what we want to do is compare the performance of these models. And the models that we'll evaluate are the small language models on one side, which are these fine-tuned Roberta models. We'll show two different variants of it. One is textual, our product, which we've trained on tens and thousands of these examples. But also to showcase the importance of good training data, we'll fine-tune a version of textual which hasn't seen any ASR transcripts. So we'll call this non-ASR textual. So we've just thrown away all of the ASR data in our training corpus to train that model. On the LLM side, we'll just take a smattering of foundation models, basically the kind of premier non-reasoning models from the big labs, and evaluate those. And to describe a little bit how we do this evaluation, I've prompted these LLMs to give these structured outputs following the schema, where basically each entity is going to be predicted as kind of a JSON object of text. So that's the substring, the label of the substring, and then the occurrence of that substring in the text. So in particular, like which Washington is it? Is it the first Washington, the second Washington, or the third Washington? That is that occurrence index. And so we'll output a list of these, and that will solve the problem of, well, potentially solve the problem of localizing text in the outputs. There we go. Okay, so we'll also provide like pre-comprehensive annotation guidelines to the model. These are basically the annotation guidelines that our internal annotators use. As an example, here's our guidelines for a given name. We have a definition as well as like kind of rules describing in detail like some of these things like prefixes, which we choose not to include. How do we treat middle names, etc. There's also a bunch of examples and edge cases, which we include, I haven't shown here, but those are all part of the annotation guidelines that the LLM is prompted with. Now, on public data, we see essentially like for this problem, the textual performs quite well and it's very fast. It beats all of these models on this particular task. Pretty substantially. The best performing model here, the best performing large language model is Gemini 2.5, which has like an F1 of around 0.84, which I would consider to be a good model, whereas all the other models never break the F1 F1 threshold of 0.8, which is what I consider to be kind of the qualitative threshold between good and bad model. So it's surprising, in fact, like, the chasm between Gemini and these other models, but also like what's worth noting is Gemini is substantially slower and substantially more expensive than any of these other LLMs. So you can achieve like reasonably good performance using large language models on this specific task of NER on this data set, but it's quite slow and it's very expensive. It's much more cost effective and much more performant and even more accurate to use a small language model here. We can break it down by entity types. It's interesting to note that the performance here on types, varies. And it's funny that essentially money becomes a difficult thing for these things to predict, as well as date times. These probably have to do with like the kind of rules around the boundaries of these spans. Names, of course, are also kind of difficult for a lot of the non-Gemini models, which is surprising, but again, probably has to do with issues around boundaries of span. So let's focus specifically on the problem of names, and let's focus this on the most difficult example of ASR transcripts, where names could occur over multiple turns of a conversation, where imagine a customer is trying to spell their name out to a support representative. So we provide very detailed rules on how to handle that, how that should be tagged. And so our model performs quite well here with an F1 score of 0.95. And essentially all these other models, fail to follow these annotation guidelines comprehensively. I mean, Gemini is almost at the 0.8 barrier here for the subtask of names, and still outperforms these other models. But again, it's very slow and expensive. If we expand the problem to talk about other PII types like payment information, credit card numbers, etc., then there are more things that we can predict, and so the scores change. Again, textual, of course, performs greater than has an F1 greater than 0.95 on this test set, and Gemini, still breaks the 0.8 barrier. It's reasonably good here, but still not like nearly as performant as your small language model that's been fine-tuned on similar amounts of data. It's been fine-tuned on lots of similar data. It's worth pointing out the LLMs haven't seen any of this data, and so in some sense it's like a unfair comparison, right? The textual model has been fine-tuned on many thousands of examples of similar data, whereas the LLMs haven't seen any of the data. They've just seen the annotation guidelines. Okay, so let's actually talk about a little more detail some of the failure modes of the LLMs and kind of like ways we could try to make the performance of these models better. Because I've shown comparison here between LLMs and our small language model, but the design space of prompts is infinite, and so I haven't proven that LLMs perform worse. I've only proven that this particular invocation of them perform worse. So we should do an earnest job of actually making these things work. And so here is kind of first analysis of the failure mode of these models to predict real entities. And so even though I've described a schema for entities, like some of the failures that happen are basically we predict a substring that doesn't occur in the text, or they'll predict a substring with an index that doesn't occur in the text. And all of these are like basically invalid, hallucinated entities in the text, which are useless. They can't be reconciled with the text in any meaningful way. And they're significant in some models, like GPT-4o has basically 5% of the entities that we that detected here were invalid. So that's not it's not very useful. GPT 4.5 does a much better job of following like the kind of instructions here and not hallucinating entities, but still qualitatively the predictions are not good. Gemini 2.5 Pro does almost as well, but overall the entities it's predicting are more correct. Okay, so like how can we make this better? Well, one of the experiments we tried was essentially like providing short versus full annotation guidelines. The short version of the annotation guidelines is basically use the sentence description of the entity, and the full guidelines were like the full thing I showed you with like rules and edge cases and examples. And we see in most of these models that there's a significant performance boost in the LLMs for using the full guidelines, except for GPT 4.1, which strangely performs worse, perhaps because it already had some sense of what it needed to do here. It was distracted by the context. The other example, which I think is kind of striking here for its strangeness, is how does performance increase when you go from 0 examples of annotated data to like few shot. So in this case, 2 examples of annotations. And basically, a lot of these models perform significantly better, with the exception of Gemini, which was our best performing model and still is, but seems to be confused by the examples we chose here. The examples were essentially carefully chosen by myself, so maybe these were not useful to the model and misaligned it. But it's worth exploring kind of this as an area for further improvement. And so maybe there's a way in using, rather than 2 examples or hundreds of examples, but some small number of useful examples to kind of boost performance of the LLM on this annotation task. Okay, so I'll stop here with just a couple of conclusions. One thing I haven't addressed, which is the fine-tuning of large language models for this task. This has essentially been answered by prior work, the Universal NER paper, which fine-tuned several like less than 32 billion parameter LLMs on the task of predicting these NER samples, and basically found that the performance of these models was sort of neck and neck with the fine-tuned small language models. So I don't see a whole lot of benefit at the moment for fine-tuning large language models on this NER task in the same way that we fine-tune small language models. It's more cost-effective and better performing to use the small language models. However, as like these LLMs are getting better and better, I think it's increasingly possible to use them as data annotators, particularly when you have humans in the loop generating test sets against which these can be reviewed. So this is something that we use in practice today at Tonic. We use LLM annotators to help extend our training corpus, and we think that this will become, well, basically this will comprise the custom model feature that we're going to release in the next year or two. Next month or two. And then finally, like obviously there's future work to do in terms of making the few shot prompting work well. And then, I think there's a interesting angle here for using reasoning models, which haven't been touched on at all. We use them internally as data annotation reviewers, and it's interesting watching the reasoning traces of these models as they kind of compare guidelines with annotations. And we found it helpful to kind of filter annotations for quality. So with that, I'll pause for questions.